Hello, and welcome back to Shiksha DaCosta. Today, we're going to learn a little bit about something called the sine function. Today, we're going to learn about the function f of x equals sine x. And you're successful when you can figure out what is the relationship between this function and the sine ratio. And you're going to do that by graphing some angles between 0 and 360 degrees. We'll explain why this is a function, and we'll define what this function actually is that we've created. And finally, we'll sketch that graph of that function when the angles are measured in degrees, and we'll figure out what are the key properties of it. To start us off, take a look at this diagram here. In this example, Julian is building a model of a cantilevered observation wheel. And you might have seen some like these. This, for example, is one of them. This is in Hong Kong, but of course, the most famous cantilevered observation wheel is the Eye of London. And Julian is building this as a project for his architecture program. His wheel is going to be next level. It's going to have a skyline view. When you're at the top, you will be able to see quite far out. And when you're at the bottom, instead of just being plain old boring, it will actually have an underwater view. So his observation wheel is actually at the edge of a dock. And as the wheel rotates, each of the pods actually goes underwater. Isn't that neat? Now, Julian's made a model for this. Of course, this is for his architecture program. And the model has a radius of 1 foot. The wheel's radius is 1 foot. And the wheel rotates by 30 degrees every minute. So we're going to imagine a situation where a guest gets on a capsule, and we're going to mark that capsule in green. And we're going to find that guest's height above the water after 1 minute. Go ahead and pause the video here and see if you can do that yourself. Well, maybe you took a look at this diagram and you said, okay, well, this model has a radius of 1 foot, so I might as well start labeling this diagram with whatever measurements I can find. So that right there is 1 foot. Okay, from the center of the wheel all the way to the green capsule, which is on the edge, which it has rotated after 1 minute, right? This only 1 minute has passed, so it has rotated about 30 degrees, and we're trying to find the height above the water. So if this is the water level, we're trying to find out what is this vertical distance. Now, as I mentioned, the rotation was 30 degrees here. So the wheel has rotated 1/3 of the way to the top, which would be 90 degrees. 30 is 1/3 of 90. How high is it above the water? Well, maybe while you were drawing this diagram, you started to notice, hey, I'm actually drawing a right triangle. This is a vertical distance that I'm measuring, and a water would be perfectly horizontal. And so those two would meet at a right angle. And in this case, if I connected the other two ends of those lines, that would create a triangle with a 90-degree angle, a right angle triangle. And because we know that this is 90 degrees and we know another angle is 30, and we even know the hypotenuse is 1 foot long, we can actually use acute triangle trigonometry. We have 3 pieces of information about this triangle. And we know that if I'm comparing the side opposite an angle to the hypotenuse of a right triangle, the sine ratio actually relates that. Sine of an angle is equal to the opposite, which in this case would be the height, divided by the hypotenuse, which in this case is 1. Okay, h divided by 1 is just h, and sine of 30 degrees is 0.5. So in Julian's model, that tells us that the height is equal to 0.5 feet, exactly half a foot, when the model has rotated by 30 degrees, which it does every minute. So we're going to start taking a look at this phenomenon right here. We're not just going to figure out the height after 1 minute. We're going to find out the height after many instances at various regular intervals. Of course, when the wheel started, 0 minutes had passed. We also want to include that in our recording. The amount of that this wheel had rotated was 0 degrees because it does 30 degrees every minute, but no time has passed, obviously. And if I wanted to draw this as a diagram, the starting point happened when the capsule was right here where all the people could step onto it. And so I might draw the diagram exactly the way you see here. The height above the water at this point was 0 meters. Now, when we figured out after 1 minute, we saw that the wheel had rotated 30 degrees. And in our diagram, it kind of looked like this. Notice that in this diagram, I've gotten rid of all of the fluff. So I've just said put the water level like around here. That's perfectly horizontal. I put the only arm that matters, the arm holding the green capsule. And I put the angle of rotation from the original starting point. And I've drawn that right triangle that we saw over here. The opposite side in purple, the adjacent side in blue, and of course the hypotenuse here in red. Also mark the angle in orange. And this is how I calculated that the height, the length of this purple line, was exactly 0.5 feet after 1 minute. What I'd invite you to do right now is continue filling out this table for 2 to 24 minutes. Take a minute here and see if you can fill out just this row for 2 minutes. Draw a diagram, write down how much the wheel has rotated, and use all of that to the the height of that triangle. Well, hopefully you realize that, well, if it rotates 30 degrees per minute, after 2 minutes, that would be 60 degrees. And so my diagram might look something like this. It's 2/3 of the way to being at the top. It's not quite at the top yet. 60 is less. But if I were to draw the right triangle the same way I did here, notice I'm still able to do that. I'm still trying to find the height. Well, now the angle is 60 degrees. And if I solve that right triangle, I find out that the height is about 0.866 feet, which is sine of 60 degrees. What about for 3 minutes? Well, at that case, the angle of rotation, this angle right here, would be 90 degrees. And if this arm rotated 90 degrees, then it would look something like this now. It would be facing straight up, and its height would be the exact same length as the arm that is rotating, which in this case we know is 1 foot long. And in fact, sine of 90 degrees, I know we can't really draw a triangle the way we did over here, but if you can imagine that this purple line is on the red line, and this blue line down here is basically 0 units long, it's not really wide at all, then you might be able to imagine an abstract triangle formed where one of the sides is 0 units long. And sine of 90, if you tried that into your calculator, you'll find out is exactly 1 foot. And that makes sense because when the road, we didn't really even have to do all of this. We already figured out that the height would be exactly 1 foot. And that's what that looks like in my very small diagram. Now I'd like you to pause the video here and fill out the row for 4 minutes. All right, 4 minutes is a little tricky. Notice that the angle of rotation has passed 90 degrees, and now it's at 120 degrees. And what that might look like is this. This is where the wheel is right now, and if it rotates another 30 degrees, its total rotation is 120 degrees. We are still trying to find the height of this triangle, or sorry, the height of the capsule. And now when we draw that line here, we can still make a right triangle with the line, with one other line being on the water. But this orange angle is no longer the angle that we need. Instead, we need a new angle that's actually inside the triangle. And this angle measure must be 60 degrees because a full semicircle would be 180. And if I remove this portion of the rotation, which was 120, I'm left with only a 60-degree rotation. So what does that mean? That means the height can be found by doing sine of 60 degrees. That would tell me the height right here. And that would be the height divided by the hypotenuse, which is 1. So sine 60, which is 0.866 feet, like we saw earlier, is the exact same as sine of 120 degrees. This is, in fact, what sine of 120 degrees actually means. It means a rotation past 90, and now we have to make the right triangle on the other side. We actually need this. This angle over here is called the related acute angle. And using it, we were able to find the height of the capsule above the water. That's 0.866 feet. Now try for 5 minutes. Well, after 5 minutes, again, the rotation would go up by 30 degrees to 150. And now, just like we did with 120, we're able to make a right triangle. So we're trying to find the height. This is the length along the water. We're trying to find this. And this height can be found by using this right triangle where I need this angle. And that angle is 30 degrees because together these two make 180. And if I remove the first 150, I'm left with just 30. And so sine of 30 degrees would be able to tell us quite easily the opposite side divided by the hypotenuse, which is just 1. The opposite side is the height, and that ends up being sine of 30 degrees, which ends up actually, if you punch into your calculator, you'll find that that is the same as sine of 150. Altogether, it's 0.5 feet. Please excuse the animations there. I do my best, of course, but sometimes it just won't cooperate. Let's try for 6 minutes. Pause the video here and fill out this row for 6 minutes. Well, after a 180-degree rotation, this is what our model looks like. And its height above the water, well, that's 0. And we can see that that's the case right here. And in fact, if you tried to put sine of 0 degrees or sine of 180 degrees, you will see that the answer is 0. That's exactly the height of that green capsule after 6 minutes or a 180-degree rotation. Once again, I apologize for that rough animation, but these are the correct diagrams for sure. Let's fill out the row for 7 minutes. Pause the video here and do that for me. Now, 7 minutes is a little tricky. Our rotation is 210 degrees. And what does that end up looking like? Well, we're already at the water. Now we're going to go a little bit lower. That angle right there is 210 degrees. Well, if I'm trying to find the height, well, the height above the water is now going to end up being a negative number. And over here, if this is the side that's along the water, still, this is a right angle triangle. But what is this angle? It can't be the whole thing. It can't be 210. But if I remove this semicircle, remember, I'm trying to find out the height. This semicircle is 180 degrees. So if I take 210 and I remove this semicircle, I will be left with just this angle, which 210 minus the 180 leaves me with just 30 degrees. And so this angle is 30 degrees in this right triangle. And to find out the opposite side, I can use the sine ratio. And sine of 210, if you check with your calculator, is the same thing as sine of a 30-degree angle, which is negative 0.5 feet. Or sorry, sine of 210 is equal to the negative of sine 30. Sine 30 is 0.5, like we saw earlier. But we know that because the capsule is underwater now, we should describe the height as a negative number. Sine 210 actually does give you negative 0.5 for this exact reason that we are measuring this vertical distance. So we looked just based off the past examples we've done, we're able to see here that the way we found the height above the water seems to be the same. We were always just taking the sine ratio of the angle of rotation. So I'd like you to pause the video here and continue going for 8 minutes, 9 minutes, all the way until you reach 24 minutes. Well, hopefully you saw that No matter what, we are able to draw the diagram pretty easily. And all we have to do, no matter what, is to take that angle of rotation and throw it into sine on our calculator. Now, in this case, you should get a negative number, of course, and that makes sense because the height is still underwater. Even after 270-degree rotation, now it's at its most underwater, which is actually -1. After 300 degrees, it starts to come all the way back around. At 330, it's almost there. And finally, 360 degrees, well, that's a full rotation. And now its height above water is right away back to 0. And notice that this number 0, that's the same thing as doing sine of 360 degrees and sine of 0 degrees. It also happens to be the same as sine of 180. Let's see what happens if we keep going. After 360, we can go to 390. And that means that we've gone all the way around once, that's 360, plus another 30. And this sine of 390 is actually the same value as sine of 30 degrees, which is 0.5. Looking one step further at 420, this is a full rotation and then another 60 degrees, which gives us the same diagram as this. And sine to 420 ends up being the same as sine of 60 degrees. Now, it also ends up being the same as sine of 120. But I wonder if that holds as much water as sine 60, especially because sine 60 actually has the same exact diagram. And that's something that I've started to notice. After 360 degrees, I'm drawing the same diagram in each of these instances. The green dot is in the same position, and the height of the green dot, therefore, seems to be the same as well. And so if I was continuing this table past 14, if I noticed this, it might be very easy for me, even without a calculator, to fill out this table. Just keep adding 30 to this row each time. Just keep drawing the same diagrams I drew over here to keep going over here. And the height of the green capsule will continue to repeat along this pattern right here. And I can extend that all the way to 24 minutes where the green capsule has rotated a total of 720 degrees, which is actually equal to sine of 0. And the way I found all of these values here is I took the angle of rotation and I did sine of that angle, and that gave me the height of the observation platform above the water. And that created, if I wanted to, and I invite you right now to go ahead and pause the video and put all of this data on a graph and see what you notice. Your graph should have ended up looking something like this. And the reason that this graph is created is because we started off with a wheel that looks exactly like this with the arm going out here. And as it started rotating counterclockwise, it started at 0 with an angle of rotation of 0. And as the angle of rotation increased, so that's the x-axis right here, the angle of rotation, the height, this point right here, went up. It went up to about 0.5 first. Then after another 30 degrees, it didn't go up to 1. It slowed down. It got to 0.866 approximately. Then it got to its maximum at 1. And then the wheel started to come down. And you're going to see that happen just now. Up and coming back down and then going back up. And when it makes its second rotation, notice the exact same graph starts to repeat. And that's what creates this function that you see here that we call the sine function. The function f of x equals sine x. That describes the vertical distance of a point from the center of a circle after that point is rotated counterclockwise after a counterclockwise rotation of x degrees, if that circle has a radius of 1. And that's quite a mouthful. But we saw that happen in action in this lesson. This is the graph that this creates is called a sinusoidal function. And sinusoidal functions have the following properties. Because a full 360-degree rotation completes and then restarts the rotation, This function is a periodic function, and it looks like this. It's got that wavy pattern. The period of a periodic function is the interval of x. So basically, how much does x change in order to complete one cycle? Sinusoidal functions also have something called an axis or a midline. This is a horizontal line that goes through the vertical middle of the function. So right about here would be the axis or midline. And it also has a property called amplitude. Amplitude is a sort of, I think surfers use this term, and there was actually a video game on the original Xbox called Amplitude. Amplitude is the vertical distance from the midline, which again would be right over here, to the maximum or to the minimum. It's always a positive number. Let's find the period, amplitude, and the equation of the axis or midline for the function f of x equals sine x. First, let's look for the period. Looking at this graph, pause the video here and see if you can figure out what is the value of x before the cycle starts to repeat. Well, I think you would have very quickly noticed that right here, that's one cycle, and that happens between 0 and 360 degrees. So the period is 360 degrees. What about the equation of the axis or the equation of the midline? Pause the video here and see if you can figure that out. So remember, the midline is the horizontal line that goes through the vertical middle of the function, and that would be the line right here. And we would always describe any line using an equation. And in this case, the equation is y equals 0. Without the y equals, you're only specifying a certain value. And in this case, the correct notation is always to put y equals. So if you were writing a test and you were asked what's the equation of the axis and you only put 0, I think you might lose some marks on that. Finally, the amplitude. See if you can find the amplitude of this function. The amplitude, like I mentioned, is the vertical distance from the midline to the maximum or to the minimum. And in this case, that is a distance of 1. It goes from 0 up to 1. That's a distance of 1. And from 0 down to 1 is also a distance of 1. So we just go from the midline to the maximum or to the minimum. And that's the amplitude. So the graph of f of x equals sine x is a wave with a period of 360 degrees, an amplitude of 1, and the equation of the axis or midline is y equals 0. In this example, I'm going to go talk about Hopewell Rocks National Park in New Brunswick. At this place, the height of the water varies sinusoidally, which means it creates a sine wave. It varies sinusoidally with time according to this function. And that looks really intimidating, but we're just gonna break this down and graph it using technology. So I won't ask you to graph this just by hand, but if you were to plug this into graphing software, then you should be able to determine all of the properties of the sinusoidal function. And by that, I also include the domain and the range. Now, this is a little tricky. So before I ask you to try this yourself, I want you to, if you were using Desmos.com, for example, you would need to go and change your graphing software to degrees mode. So on Desmos.com, you would have to click on that gear and then change it to degrees mode. Otherwise, you'll get a really wacky graph. Once you've done that, this is the graph that you should be able to generate just by typing this into your graphing software. The independent variable is t. The function is h at t because we're measuring the height of the water according to time. That's the height of the water, and that's time in hours. So what is the amplitude period equation of the midline, the domain, and the range? Well, it's easiest to start with the maximum, which in this case is 11, and the minimum, which is 2. Knowing these two values, do you think you'd be able to find the domain and the range? Pause the video here and see if you can do that. Well, if I were trying this, certainly the domain looks like it could be any real number. And of course, time can be any real number, even decimals or irrational numbers. But the range, I need the minimum and the maximum to find that. The lowest this function gets is 2, and the highest is 11. So the height of the water can be represented by h of t, as long as h of t is greater than 2 and less than, or sorry, greater than or equal to 2 and less than or equal to 11. And of course, the height can be any real number in between there. Now see if you can find the equation of the midline. Well, the midline is the line that goes right through the middle of the function. So that would be right over there. And it's kind of hard to estimate. Is that 5 and 5.5? Is it 6, 6.2? The easiest thing to do would be, well, if I know the number is right in the middle of the maximum and the minimum, how do I find a number that's between two numbers? Simply take the average. So we add them together and we divide by 2, and that would give me 6.5. So the equation of the midline is y equals 6.5. Now pause the video and see if you can find the amplitude. Like I mentioned, the amplitude is just the distance between the midline and the maximum or the minimum. And of course, the midline we know is at 6.5 now. And the distance to the maximum of 11 would just be 11 minus 6.5, which is just 4.5. And if we did the same thing here, 6.5 minus 2, we would also get 4.5. So the amplitude is the same in both directions. Finally, pause the video one last time, and see if you can find the period of this function. Now, this is quite easy. And in fact, I could measure from here to here and say, oh, that's 12 hours. But if you were a little bit stuck on the fact that the sine function starts on the midline and it starts by increasing, you could also notice that this is one complete cycle. And if you ever want to find out how long it takes, you can always take the end of the cycle, the independent variable, which in this case is 15, and you can subtract the beginning of the cycle, in which this case it's 3. 15 minus 3 also would get us 12. Even though it would have been easier to go from 0 to 12, I just thought I'd do this to show you that you can even start at any point, and as long as you complete one complete cycle, you can just subtract those two x values to find the period. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.